Today, I invite you to join me on a captivating journey through time and space as we explore the life story of our universe, from its fiery birth in the Big Bang to the various scenarios that might one day signal its end. We'll delve into complex concepts, but don't worry, I'll guide you through them with clear and simple explanations, ensuring a comfortable and enlightening experience. Our story begins approximately 13.8 billion years ago with an event known as the Big Bang. Imagine a time when all the matter, energy, and even space itself were compressed into an incredibly hot and dense point. This singularity was unstable, and in a fraction of a second, it expanded explosively, giving birth to the universe we inhabit today. This wasn't an explosion in space. Rather, it was an expansion of space itself, carrying galaxies, stars, and planets along with it. In the initial moments following the Big Bang, the universe was a seething, opaque plasma of fundamental particles, quarks, electrons, and photons, all interacting at extremely high energies. As the universe expanded, it cooled, allowing these particles to combine and form protons and neutrons. This process continued, leading to the formation of simple atoms like hydrogen and helium. With the universe becoming more transparent, light could travel freely, and the first photons began their journey across space. We can still observe this ancient light today as the cosmic microwave background radiation, a faint glow permeating the universe and providing a snapshot of its early state. As millions of years passed, slight irregularities in the density of matter led to gravitational attraction, causing gas clouds to collapse and form the first stars and galaxies. These stars acted as cosmic furnaces, forging heavier elements in their cores through nuclear fusion. When massive stars exhausted their fuel, they exploded as supernovae, dispersing these elements into space. This enriched material became the building blocks for new stars, planets, and eventually life itself. Our own solar system formed about 4.6 billion years ago from a rotating cloud of gas and dust. Under the influence of gravity, this cloud collapsed, with most of its mass concentrating to form the Sun. The remaining material flattened into a disk, where particles collided and stuck together, gradually building up the planets, moons, and other bodies that orbit the Sun today. For a long time, scientists believed that the gravitational pull of matter would gradually slow the universe's expansion. However, in the late 20th century, observations of distant supernovae revealed a surprising truth. The expansion of the universe is not slowing down, it's accelerating. This discovery was both shocking and intriguing, suggesting the presence of a mysterious force driving this accelerated expansion. Researchers have named this enigmatic force dark energy. Unlike the gravity that pulls objects together, dark energy seems to have a repulsive effect, pushing galaxies apart at an ever-increasing rate. Despite its significant influence, dark energy remains one of the greatest mysteries in cosmology. We don't yet understand its nature or origin, but its existence has profound implications for the ultimate fate of the universe. The destiny of the universe is a topic of much speculation and research. Several theories attempt to describe how the cosmos might evolve in the distant future. Let's explore some of the most discussed scenarios. In this scenario, the universe continues to expand indefinitely. As galaxies drift further apart, stars exhaust their nuclear fuel and cease to shine. New star formation becomes rare as the necessary gas is used up or dispersed. Over unimaginable timescales, even black holes evaporate through a process known as Hawking radiation. The universe approaches a state of maximum entropy, where all energy is evenly distributed and no organized structures remain. In this cold, dark, and dilute cosmos, life as we know it would be impossible. Alternatively, if the density of matter in the universe is sufficient, gravitational forces could eventually halt the expansion and reverse it. Galaxies would begin to move closer together, leading to collisions and mergers. As the universe contracts, temperatures would rise, Stars and planets would be destroyed, and matter would be compressed into an increasingly dense state. Ultimately, all matter and energy could collapse back into a singularity, possibly leading to conditions similar to those at the beginning of the Big Bang. Some theories suggest this could trigger a new cycle of expansion, a cosmic rebirth. This more dramatic scenario depends on the nature of dark energy. If its repulsive force increases over time, it could reach a point where it overcomes all other forces, including gravity and even the forces holding atoms together. In this case, galaxies, stars, planets, and eventually all matter would be torn apart. Space itself would be rent asunder in a catastrophic event known as the Big Rip. The timeline for such an event is uncertain and would depend on the properties of dark energy, which are still not fully understood. Some cosmologists propose a cyclic model of the universe, where the current expansion is just one phase in an endless series of expansions and contractions. In this Big Bounce scenario, the universe could eventually stop expanding and begin to contract, leading to a big crunch. However, instead of collapsing into a singularity, conditions could become suitable for a new Big Bang, initiating another expansion phase. This cycle could repeat indefinitely, suggesting that our universe is eternal, with no true beginning or end. To understand these potential fates, it's essential to delve deeper into the concepts of dark energy and dark matter. Together, they constitute about 95% of the total mass energy content of the universe, yet they remain largely mysterious. As mentioned earlier, dark energy is the term used to describe the unknown force driving the accelerated expansion of the universe. It's thought to be a property of space itself, causing a repulsive effect that increases as the universe grows. The exact nature of dark energy is still a subject of intense research. Some theories propose it could be a new kind of dynamic energy field, while others suggest it might be a cosmological constant, an inherent energy of empty space. While dark energy drives the expansion of the universe, dark matter plays a crucial role in holding structures together. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it invisible to current detection methods. However, its presence is inferred from its gravitational effects on visible matter, such as the rotation of galaxies and the motion of galaxy clusters. Dark matter acts as a cosmic scaffold, providing the gravitational pull needed to form and maintain the large-scale structures we observe in the universe. Advancements in technology have allowed astronomers to observe the universe with unprecedented precision. Space-based telescopes, such as the Hubble Space Telescope, and ground-based observatories have provided valuable data on distant galaxies, cosmic microwave background radiation, and supernovae. These observations have been instrumental in shaping our understanding of the universe's expansion and the roles of dark matter and dark energy. Future missions and experiments aim to shed more light on these mysteries. Projects like the James Webb Space Telescope and the Euclid mission are designed to probe the nature of dark energy and dark matter, map the large-scale structure of the universe,